All right. The natural numbers we're going to denote with the letter N, capital letter N. The whole numbers, capital letter W. Integers, capital letter Z. Rational, capital Q. Irrational I. And real will be R. Different textbooks will do it differently. For our purposes, this is how we're going to do it. So make sure on your sheet you have all of them listed, plus what letter we're going to use to denote those sets. All right. All right. So what are the natural numbers?
I didn't get to write all those down.
Oh, sorry. There you go,
Sorry.
Charlie. No, you're good.
I'm trying to be quick.
Are we allowed to take pictures of what you write down?
Oh, yeah. You can take pictures.
Or
Now, one
like,
thing I will prefer, you can take pictures. This will also be in a recording, but you need to be taking notes.
yeah, I'm
Um,
taking notes
part
just in
of
case.
Yeah,
Uh,
part of your learning process is pen to paper. It embeds it in the mind. So, but yeah, feel free to take screenshots.
I've written everything so far, just in case like I missed something.
Yep, no worries.
Thank you.
You guys
Okay.
good? All right. First, natural numbers. Natural numbers are going to begin with the number one, and then every natural number is derived by adding the number one. So if I add one to one, I get two. Then if I add one to two, I get three. If I add one to three, I get four, so on and so forth. Anytime in math that you see three dots like this, that means continuing in the same pattern. Continuing in the same pattern. So this is the entirety of the natural number set. It begins with the number one, you add one out to infinity. So the number 12, the number 6 million, those are natural numbers. The number one half, not a natural number. You cannot get to a half by starting with one and adding one. Any decimal, 0.562, not a natural number. Okay, they're called natural numbers because this is how we learn to count. As little children, we began with the number one. All right. Next, we have the whole numbers. The whole numbers start with zero. Then they include all of the natural numbers. So believe it or not, it took civilization a lot of time to come to the point where they understood that they needed a zero. For ancient people groups, zero was um, irrational. Irrational in the sense of there's no such thing as nothing, right? There's always something. And so zero really wasn't a concept. And it developed actually as a placeholder, like the number 100, where you have two zeros after a one. Um, but when zero was invented, it's a much bigger deal. We obviously grow up understanding it, but it's a pretty big deal, the idea of nothing. So the only difference between natural and whole is that zero. All right, let's move on to the next one. All right, integers And let me write this out first before you write it down because I'm going to kind of go to the left here because I need to do something. All right. So it's also 0 in all the natural numbers, but it also includes the opposite of all the natural numbers. Okay. So in mathematics, the minus sign means opposite. So, for example, the number 5, if I were to say the opposite of 5, another way to say the opposite of 5 would be -5. Does that kind of make sense? Then, if I were to say the opposite of -5, well, that brings me back to 5. So in math, the minus sign also means opposite. So the opposite of all the natural numbers, 0, and the natural number. So what does this look like? This would look like -3, -2, -1, 0, 1, 2, 3, so on and so forth. Does that make sense? Okay. So any integer is any natural number, its opposite, or 0. So the number 0 can be either an integer and it can be a whole number, but 0 cannot be a natural number. The number 1 can be a natural number. It can also be a whole number. It can also be an integer. The number -1 can be an integer, but it cannot be a whole number, and it cannot be a natural number. All right. Now let's talk about rational numbers. Rational numbers are denoted by the letter Q. All right. A rational number is any number that can be represented as a ratio of two integers. Okay, this is a z over a z, meaning an integer over an integer. So if I had, for example, the number 1/2, that is a rational number. Why? Because 1 and 2 are both integers, and they're in a ratio. So the number half can be a rational number, but it cannot be an integer, it cannot be whole, and it cannot be a natural. The number 1/2 can only be, so far from what we've learned, only be a rational number. All right. Next we have irrational. And this one's harder to explain. For right now, let's just say not rational. Okay? That'll cover for what we need right now. Not rational. Now, an irrational number, what does that mean? That means I cannot represent it as the ratio of two integers. Well, what is a number that I cannot represent by the ratio of two integers? Well, one example is the letter pi. Pi can be estimated as 3.14 15926, blah, 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 so on and so forth forever. There is no repeating decimal within pi. Pi, the number of decimals that it goes out is infinite, and they do not follow any pattern at all. Meaning that we have no way of representing pi accurately with numbers. That's why we use a Greek letter. So this is an example of an irrational number. I cannot represent pi using the ratio of two integers. If you take 22 over 7, for example, and divide that, you'll get 3.14 something, but it will not be exact. This is about as close as we can get. All right? So certain numbers follow this trait. If I take the square root of the number 2, that is also irrational. There's no way to represent that as a fraction, the ratio of two integers. That is irrational. So, one of the reasons why the circle was such a unique mathematical invention, or not invention, but discovery, was they noticed, if you remember from what we know about a circle, let's say that this is 2 meters, we'll say 3 meters in diameter. 3 meters in diameter for a perfect circle. The circumference is pi times diameter, right? So if I divide both sides by diameter, pi is always equal to the circumference of the circle divided by the diameter, okay? This is when pi was discovered. They could take a perfect circle with a piece of string, and then they could measure the diameter. Then they would take that string and they would elongate it so they could measure the circumference. And what they found was one of these two always had to be irrational. Either the circumference was irrational or the diameter was irrational. So in this case, because my diameter is a perfect 3 millimeters, my circumference would end up being irrational. In this case, 3 times pi. So the circumference they would measure as 3 pi. So it was a fascinating discovery within the ancient mathematical world. All right, irrational numbers. Now your final one is real. Real numbers are all the numbers that you're going to interact with. So they include the rational and the not rational. Rational and not rational. So this includes the natural, the whole, the integer, the rational. Sorry, the integer is a z, the rational, and the irrational. All of those are included in what is called the real numbers. So every number that you probably know at this point in your mathematical development is classified under the real numbers. When we get to Algebra 2, that's when you'll start learning numbers that aren't real. All right, any questions so far? All right. So let me do a couple of examples. You guys can do these on your paper. We're going to do 25 over -5. All right. And what we want to know is, okay, how many of these sets does this number belong to? All right. How many sets does this number belong to? This is a 25 over a -5. All right. Is it a natural number? It cannot be a natural number because I have a negative. And no negative number is a natural number. Natural numbers begin with the number 1 and increase by 1. Is it a whole number? It cannot be a whole number because it is not 0 or a natural number. Can it be an integer? Yes, it can. This is the number -5. 25 divided by -5 is -5. And -5 is an integer. Is it rational? Yes, it is, because I can represent -5 as 25 over -5. I can also represent -5 as -25 over 5. You only have to demonstrate that you can represent the number as a ratio of two integers for it to be a rational number. Is it irrational? It is not. It's a perfect number. It's, well, not perfect number, but it is a whole number. All right. Is it real? Yes, it is a real number. All right. Let's do another one. Let's do the number 0. Go ahead and put down what you think it is on your paper, and then I'll go through and give you the answer here in about 20 seconds. Right. 0 is not a natural number. It is a whole number. It is an integer. It is rational. It is not irrational. And it is real. All right. So, James, is that you that just joined us? I think it is. If you're talking, James, it is muted. All right, we'll keep going here. We're going to assume James is on the other side of that. All right. All right, so part of your homework is going to have basically you're going to have a number and then you're going to determine what sets that number belongs to. All right? All right. The other thing I want to do, and I understand that a lot of this is going to be review and you might be bored to tears, but that's okay. We need to start with a good firm foundation. And we want to talk about each one of our operations. So the 4 operations we're going to talk about are addition, subtraction, multiplication, and division. All right. Addition, pretty straightforward. You're just combining 2 ideas together, right? I can add things in any order that I want, whether I have 2 plus 5 or 5 plus 2. Regardless, it is 7 on both sides. All right, subtraction. And what we're going to find, guys, is that subtraction, addition, and division are just different forms of adding, okay? So subtraction is adding a number's opposite. Adding a number's opposite. So a plus -b, and we'll give that a 2 plus a -5. When I add an opposite, if we look at the number line, we start with our first number, which is 2. Okay. Now I'm going to add. If I add, I go up the number line, which is to the right. If I subtract, I go left on the number line, which is subtracting. But in this case, I'm going to add the opposite of 5. So what that means is whatever direction I'm going, I have to go the opposite direction. So from 2, instead of going to the right 5, I'm going to go to the left 5. 1, 2, 3, 4, 5. So I would land at -3. And this is what is known as the definition of subtraction because 2 minus 5, 2 minus 5 is -3. And 2 minus 5 is a more efficient way of writing 2 plus a number's opposite. Does that make sense? If we were to look at this, now that's very abstract sounding. If we were to look at this in terms of money, right? So if you have $2, but then you owe somebody $5, right? You're in the hole $3. We understand that. I have 2, but I owe you 5, so now I'm in the hole 3. I can pay you 2, but I still owe you $3. Okay. The other way to look at that is you have $2 and you're going to give somebody negative, or you're going to basically add to yourself -$5. That's essentially what you're doing, is you're combining yours with another thing, because that's what we do in addition. We combine two ideas. So we're combining 2 with a -5, and that combination results in -3. That is subtraction. All right. A multiplication is a way of combining numbers more efficiently. So for example, if I did 3 times 5, this is the same thing as saying 3 plus 3 plus 3 5 times. 3 plus 3 plus 3 plus 3 plus 3. But we didn't want to sit here and do that over and over and over. So we came up with the idea of multiplication. And what is multiplication? Multiplication is broken into two numbers that are two different ideas. Okay? The first number is things. The second number is groups of things. So what do I mean by that? Well, the first number is 3. I have 3 things. Okay, I've got 3 things. But I have 5 groups of these 3 things. So 1, 2, 3, 4, 5. Here are my 5 groups of the 3 things. So if we think about this physically, if I were to take a box and I had 5 boxes, 1, 2, 3, 4, 5. And inside each one of those boxes, I put 3 marbles. You still have 5 boxes, but notice that our things, I have 3 things inside 5 groups of those 3 things. So how many marbles do I have total? I have 15 marbles. This is a way of adding, but in a more efficient way by creating multiplication. Now, if I reverse the two numbers, and if I do 5 times 3, I have now changed my things and my groups. Now I am adding the number 5 3 times. So instead of having 5 boxes, I now only have 3 boxes. But each one of those boxes has 5 marbles. And that also equals 15. So notice how we have the exact same number of things, regardless if we interchange the number of things and the number of groups, we will always result in the same number of things. So whether I have 9 groups of 2 things or 2 groups of 9 things, we always end up with the same number. This gives rise to you don't have to know the name of it. We'll go over it another day, but what's called the cumulative property of multiplication, that I can multiply things in any order I want. Just like addition, I can add things in any order I want. All right. All division does is it creates the inverse of multiplication. So what it does here is it says, if I've got 15 things and I divide it into 5 groups, how many things do I have per group? You have 3 things per group. If I have 15 things, but I divide it into only 3 groups, well, now you have 5 things per group. So it inverts what we do with multiplication. Multiplication says groups of things equals things. Division says things divided by the groups gives you the things. You can also do things divided by things, and it gives you the number of groups. So if I said I had 15 things and I had 3 things per group, it would give me 5 groups. Never knew there was so much to addition, subtraction, multiplication, and division, did you? But I can tell you're bored, so we will move on. All right. Let's see how much time we got. Just a few more minutes. So let's cover another form. So remember we did 5 times 3. So 5 added together 3 times. Now we're going to look at 5 to the 3rd power. Instead of adding together 3 times, I am multiplying together 3 times. So 5 plus 5 plus 5, which is 5 times 3, that's 15. But if I do 5 to the 3rd power, that's 5 times 5, which is 25, times 5, which is 125. And all the power means, and within an exponent, so let's break this down. I'm going to write really big so we can get all the terminology down here. The 5 is what's known as the base. The 3, that is what's known as the exponent. And the whole thing together is known as the power. So sometimes you'll hear people say 5 to the 3rd power, 5 to the 5 cubed. Sometimes you hear the word cubed for 3. But what all that means is that 5 is my base number, 3 is my exponent, and 5 to the 3rd is my power. So what does this mean? This means that we are multiplying the number 5 by itself 3 times. Just like multiplication, we are adding the number 5 to itself 3 times. In exponents, we are multiplying 5 to itself 3 times. Okay, so this is kind of the nomenclature of one. All right, any questions so far?